Hello, and welcome back to another session on data mining. In this part of the lecture, what we are going to do is try to build a deeper understanding of what actually happens when you apply a transformation on a given data set. To understand that, let's take a data set. Let's just take 2 points in two-dimensional feature space, our favorite feature space because it's easier to draw. Let's say we have a point over here with the value of, I'm going to call this point 1. And the feature values for this are, let's say, -1 and -1. And then let's say we have got another feature point over here that I'm going to call point 2, and its corresponding feature values are, let's say, +1 and +1. Okay. So these, let's say we have got these 2 points. Let's apply a transformation on these points. And the transformation that we are going to apply is going to transform a given point x in the following way. It's going to take the square of each of the individual features. Okay, so if you take the square of this uh, point, that is point 1, then that is going to get mapped to 1 1 because the square of -1 is 1. Whereas for point 2, it's going to remain the same, right? So it's going to be still be 1 1 because the square of 1 is going to be the same. So in the transformed space, I'm going to use a different color for the transformed space just to discriminate it. So let's use blue. Let's say we've got these points in this space, then what we get is this point over here, point 1 gets mapped to 1 1, and the other point also gets mapped to 1 1. So both of these points in the transformed space get mapped to the same point in this space, right? And that's really easy to understand. Now, if we calculate the distance between these points before and after transformation, we see that these points, and for distance, I'm going to use another color. Let's use purple. Let's say the distance between these 2 points is this much, right? And we can calculate how much distance there is by simply using the Euclidean distance formula. We can calculate the distance between them by subtracting the first element of this from this. So that's going to give 2 squared plus 2 squared square root. And then that is going to give us a square root of 8. So that is the distance between them. You can go ahead and calculate it yourself. But after the transformation, these 2 points, both of them are being mapped to the same location. Therefore, the distance between these two is 0. So what we have seen is that transformations, they change the, the distance, the concept of distance between 2 points. And that is how they are able to achieve these folds. Okay, and that is how we have been able to verify that these can solve linearly non-separable problems using a linear discriminant. Okay, so we've chosen a particular transformation and we verified that after the transformation, the data set is linearly separable, whereas it was not linearly separable before the transformation. We have also a code for that, and I have already provided that to you, and you are welcome to play with it. This is just a more detailed understanding that transformations in the feature space change the definition of distance. One key requirement of such transformations is that they're only based on the distance, or based only on the features of the original features and not the labels of the examples. And that is important because for a given test example, we need to apply the same transformation on that. And for that, we don't know the label of that. Therefore, we won't be able to use the transformation if it is based on labels. So we never use any label information while we're making these transformations. But the effect of these transformation is that a feature transformation makes a change in the distance. And this is going to be the mathematical proof of this, whereas I've previously given you a geometric proof of the same thing. Okay, so understanding one of the two is fine. But what I welcome you to try to do is, before we walk towards that proof, I welcome you to explore these problems. So there are 3 different linearly non-separable classification problems on your screen, and I welcome you to find transformations for each one of them that would make them linearly separable. So find phi of x that would make this problem linearly separable. The same thing goes for this one, and same thing goes for this one. So please go ahead and try to do that. Now let's come back after that slight deviation from our original plan. Let's talk about how we can prove that feature transformation actually change the concept of distance, and it's really simple to understand. Let's say we define the distance between 2 points as DAB. then that distance can be expressed as the norm of the vector A and from vector from B to A. So let's say we've got 2 points, A and B. Let's make this point A, and let's make this point, let's say B. We know that these two can be represented as vectors. This is going to be A vector, and that is going to be B vector, and this is a distance between them, right? And that distance is nothing but the length of the vector of this vector, right? That you see from B to A. And that is how we represent length or distance. And then we also know that that can be written as this way, because we know that the square distance or the square norm of a vector is nothing but A transpose A. And that's what we have applied over here. The square of this norm, or the square distance, is equal to A minus B transpose into A minus B, and that comes out to be A transpose A plus B transpose B minus 2 times A transpose B. Okay. After the transformation, this concept of distance between them gets changed. So point A is mapped to phi of A and point B is mapped to phi of B. And if we calculate the distance now, we can pretty much use the same formula, and then that gives us this definition of distance, which is different from this definition, unless uh, phi of A retains is an identity transformation. Okay, so we've seen that, and we have a pretty good intuitive understanding now of how applying a transformation can change the definition of distance in the feature space, right? But if we look at this formula in a bit more detail, we see that the distance between, or the square of the distance between A and B is equal to A transpose A plus B transpose B minus 2 times A transpose B. And this is a dot product, right? This is a dot product, and this is also a dot product. So this is a dot product of A with itself, this is a dot product of B with itself, and then we've got a dot product A and B. So we see that distance can be expressed in terms of dot products, or distances and dot products are nothing. They are very closely related to each other. So we can, if we are given dot products, we can go back to computing distances and so on. So the point that we're trying to make here is that distances can be expressed in terms of dot products, right? When we make a transformation, what happens is that instead of dot product in the original feature space over here, like A transpose A, we are now taking a dot product in this transformed feature space, right? So if you see, instead of A transpose A, we have phi of A transpose phi of A, and then we've got the same thing for B, and then we've got the thing for A. Instead of having A transpose B, we have got phi of A transpose phi of B, okay? So that means that whenever we do a transformation, that changes the concept of distance, right? And that would also change the concept of dot product between them, right? Because dot product and distance are related to each other. And we have a formula for that that's right on your screen over here, right? So that means, if you think about it in a bit more detail, if we change the definition of dot product, then that would change the definition of distance. Let's say instead of defining dot products like the way we typically do as A transpose B, if I change the definition of dot products like this one, so that first I apply a transformation of A and then take a transpose, and then I do the same thing with B, then the distance is going to change. Or in other words, let's say if I, instead of defining the dot product like this as the dot product that you see on your screen, let's say if I change the definition of the dot product to a different formula, let's say if I start doing dot products like this, A transpose B squared, then that is also going to change the concept of distance between these points, and that is going to be equivalent to having a transformation, an implicit transformation. So just to present a brief recap of what we've done so far, we've talked about that folding the folding the feature space allows us to do discrimination or classification with a single cut for data sets that are not linearly separable. And we've seen that we can achieve this folding by changing the definition of distance. And one way of changing the definition of distance was to use transformations. We have done a proof of that, right? And what we have seen so far is transformations change the concept of distance. So if you apply a transformation on a given point, and on another point, the same transformation, then we have a change of distance between these points. And we know that distance can be expressed in terms of dot products. That means if I change the dot definition of dot product, then what would happen is if first it would change the definition of distance, and then it would change and then it indicates that there would be a implicit transformation. Or to put it shortly, changing the definition of a dot product, if we use a different dot product definition, then that is another way of changing or folding this feature space. So instead of doing an explicit transformation, if I change the concept of dot products in a given for a given feature space, then that automatically means that I've applied a transformation. And next, what we are going to try to do, what I'm going to try to explain to you is, is to give a proof of the transformation that we've been using and how it's related to a dot product. Okay, so let's say we've got two-dimensional data. Let me turn on my pen, please, here. Okay. So let's say we've got two-dimensional data. We've got 2 points. We've got a point A, and that is represented as A1 and A2. It has two features. And then we've got another point B that has two features. Let's say we've got B1 and then we've got B2. So we've got these two vectors, A and B. And that this is the classical definition of the dot product between these 2 points. A transpose B is equal to A1 B1 plus A2 B2. Very simple, right? If I change the definition of dot product from the way it is written right now into what is called a kernel function, and I'm going to indicate, so this is going to be a generalized dot product. So let's say if I change the definition of dot product from the simple Euclidean dot product, A transpose B to A transpose B squared, you can even take a cube if you want. But let's stick to a square for now. If I change this definition, the definition of dot product to this thing, then what we get is A1 B1 plus A2 B2 squared, whole squared. Okay, so this is the new definition of the dot product. And if you remember, when we were solving the exclusive OR problem, we talked about a transformation that maps the first feature to the same thing, the second feature to the same thing, but takes the product of the first and the second feature and introduces a third feature. So this is the transformation that we've been talking about when we were solving the exclusive OR problem. Now, after the transformation, if I apply this transformation on point A, then I get A1, A2, square root of 2, A1, A2. And then if I apply this transformation on B, then I get B1, B2, square root of 2, B1, and B2, right? And if I take the dot product after the transformation, then that comes out to be A1 multiplied by B1, A1, B1, plus A2, B2, plus this square root of 2 gets multiplied with this square root of 2 and turns into a 2. And then we get A1, A2, B1, B2. And if I just do some rearrangement of this, then I can write it like this one, right? A1, B1 plus A2, B2 squared, right? Which is exactly the same thing as this new dot product definition that I had, right? So this is a sort of a proof by example of how transformations change the definition of dot product, or in order to do a transformation, or another way of doing a transformation is to change the definition of dot products. If you haven't been able to follow all of this, it doesn't really matter much. Because if you are able to understand this concept that folding of the feature space is important so that we can use a linear discriminant or a straight cut to achieve linear separability over linearly non-separable data sets, then essentially we need to do the folding, right? And to do folding, we can change the definition of distance. And if I change the definition of distance, that is equivalent to folding. If I change the definition of dot product, that is another way of doing the same thing. That is folding in the feature space or warping the feature space. The third way is, of course, to to apply an explicit transformation. And what we've seen so far is all of these methods are exactly equivalent to one another. If you do a feature transformation over the original features, that corresponds to changing the distance. We've seen whenever you do that, you change the distance. And then I've shown you that if you change the definition of the dot product, that is equivalent to the transformation, to transforming the original data points. So this is the proof right in front of you. And both or all three of these ways, if I change the definition of distance, if I change the definition of dot product, or if I apply a transformation, should now enable us to do nonlinear classification. However, the most generic way of doing a transformation is to apply it at the lowest end of this spectrum or at the lowest level, and that is to change the definition of dot product from a regular dot product in the Euclidean feature space, which is A transpose B, to a generalized dot product, which is called a kernel function. So what I'm going to say here in this box is going to be very important, and that is folding of the feature space, changing definition of dot product, changing dot products, changing distance definitions, and doing feature transformations. All of them are exactly the same thing, or they have the same effect. So I hope you get you wrap your head around this, and there are different ways of doing this, of explaining the same thing. If you go and read a book about it, some people start with definition of the dot product, and then they talk about how that relates to transformations. But don't be confused. All we are doing is changing the, the definition of distance or folding a piece of paper. This is how a fold in that we've just done can be expressed mathematically. It can be expressed in terms of changing the definition of the dot product or changing the distance or doing a feature transformation. Thank you.